Hello everyone, here is Andrea, and in this video we're going to learn some other very useful function of SymPy, which will allow us to uh, do some more advanced kind of tasks, or always math related tasks, and more precisely we'll use SymPy in this tutorial to calculate derivatives of a function, both normal derivatives and partial derivatives. Um, we will learn how to calculate like the integrals of a function, how to calculate the limits, and also we will see that SymPy can also be used to directly plot uh, functions on your directly from your terminal. Of course, as I already did a video on SymPy in which I showed the main basic functions of SymPy and how to initialize a SymPy session, how to define a variable, how to define a function. I will not cover those topics here. I will just, let's say, take them for granted. If you're not sure about those topics, or you just simply not remembering how to do those things, just have a look at the previous article or the previous tutorial in which I show all those functions. So I think we could just start directly. I will type all the comments in my terminal here, so I can just move this up here. But of course, as I told you last time, all the comments that I will type in the terminal can be typed as well on your script with the same result. The thing that is basically changing is just the graphical output, but from a functional point of view, it's just the same thing. Um, so as I said, as you may already know, SymPy allows you to do to calculate mathematical function and to solve them both symbolically and numerically. So yeah, I will just start to let's say, yeah, we'll start with the first section, and I will show you in this section how to calculate derivatives of a function and the partial derivatives. Well, derivatives, as you may already know, are quite important since they allows you to basically, if you have a function, to calculate the minima and the maxima of that function, which are in some data science related topics or problems, are very important points which could be useful to identify. But also, I mean, just from a mathematical point of view, being able to calculate the derivative of a function both symbolically and numerically, it could be a quite nice thing to know. So just to start, I'll start my terminal with Python. I will import SymPy. Perfect. And then I will initialize the SymPy session. So sympy.init underscore session. Perfect. So I initialized some functions and some variables here. Perfect. So let's begin by defining a function. So f equals to, let's say, 3 times x squared plus 4 times x plus 5. So this is f. We can just print it to see this is the function. And so to calculate the derivative of this function, the SymPy function that we will use is called Diff, like this, and we just have to pass as the input parameter the name of the function that we want to calculate the derivative, or that we want to differentiate, which basically means the same thing. So f, close parenthesis, and that's it. Here is the derivative of this function. So 2 times 3 is 6 times x, and then of course the derivative of 4 times x is 4, while the derivative of 5, which is just a number, is 0. In this example, I didn't specify any variable because I had just a single variable. But in some cases, for example, I could be also interested of calculate not just a simple derivative, but like a second order derivative or third order derivatives or so on. So, for example, in this case, I could still differentiate this function in getting a result different from zero. So let's say that we want to calculate the second derivative of this initial function, so f. To do that, we can use the same function, so diff, but we have to specify some additional parameters. So let's say f is this one, just to have it right above the solution. I will just type diff, passing in the name of the function, so f. Then I have to pass in the variable with respect to which I'm going to differentiate the function. So in this case it's x. And then I can just type in the number of times that I want to calculate the derivative. So the second order derivative simply means that we're going to calculate the derivative of the initial function twice. So let's say, for example, the second derivative, so 2. And yeah, we get 6, which is the derivative of this function here, or the second derivative of this function, the initial function there here. So this is it. This was the second order derivative. If we were interested in calculating like the third order derivatives or higher order derivatives, we just had to change the number here. So that was it. Another useful thing related with derivatives is the possibility to calculate partial derivatives. Partial derivatives are similar to the normal derivatives, but we have to we use them when we have a function that is expressed with multiple variables, like a 3 or 2 variable function, and we want to calculate the derivatives just with respect to one of the different variables that are present. And so to do that, the procedure is really similar to the one that we have just seen so far. So just to give you an example, let's define another function which is dependent on more than one variable. So g, for example, 2 times x plus 4 times y, let's say square, and yeah, let's say minus x times z. So it's a 3 variable function. This is g. And to calculate, let's say that we are interested in the derivative of this function with respect just to x. We just type diff g, comma, and then we specify the variable, so here, and then we get the results, the symbolical results. So we have basically calculated the derivative of g with respect to x, so 2 here from here, and then this has not any x dependence, so it's 0, and then here the only x dependence is here, so the derivative of this part will be minus z, and here we have the result. As in an analogous way, we can calculate the derivative of g with respect to y, and only this term will contribute to the derivative, so we have y squared, so it will be 2 times 4 times y, so here 8 times y, and then just to conclude, the derivative of g with respect to z, it will be minus x, because we have just this term here. So perfect. I think that this was it for the derivatives. Now we can switch to the opposite operation of the derivatives, which are the integrals. Usually integrals are used when we want to calculate basically the integral of a function, is because most of the times we're interested in calculating the area beneath the function, or the area between the function and the x-axis. But of course, in physics and even in mathematics, the integrals have a lot of other meanings and are used quite a lot. They are really important functions, but I mean, calculating an integral is not always that easy as, for example, it is calculating a derivative. So I think that for this task, especially for this task, SymPy is really useful for its capability of calculating integrals and evaluating them both symbolically and numerically. So let's just define a function. Let's call it, we can use maybe the same function as before, so f, let's see, yep, it should be fine. So if I want just to define the integral of this function and basically expressing it in a symbolical way, I can use the function called integral with the capital I, integral. And I have to specify, as usual, the function that I want to integrate, which is f. And then, if I wanted also to specify the boundaries from between which I want to calculate the integral, or to express, in this case, the integral, I will just have to open other two parentheses and specify the variable, which is x, and then the boundaries, which is -2, 2, close the parentheses, and then, as you can see, if I print it, this is the expression that I just wrote here. So the integral between -2 and 2 of f, which is this function, with respect to x. So the differential here is referred to x. So in this case, I didn't solve the integral. I just expressed it in a more, let's say, fancy way from a graphical point of view. If I want to solve actually the integral, we have to change the function. We will not use integral as a function. We use a similar function which is called integrate. So basically, yeah, let's just do it. Integrate. So we will first solve the function the integral symbolically. So just f without specifying the boundaries. So as you can see, I just entering the name of the function that I want to integrate. So integrate f, and this is the integral. So x to the x cubed plus 2 times x squared plus 5 times x, which is the integral of this function here. Well, if I wanted to calculate actually the value of the integral between these two boundaries, I can still use the function integrate, but then I have, as I did before with the derivatives, I have to specify within parentheses the variable with respect to which I want to integrate the function and the boundaries. So -2, 2, closing the parentheses, and the result is 36. So this is the result of this integral here. So perfect. Sometimes in more, let's say, advanced calculus tasks or problems, we may also have to calculate like the double integrals or triple integrals, which are basically integrals with multiple integrals refer to multiple variables. So they are really hard, I think, to solve, especially to solve them by hand. So for this reason, we still use SymPy, which again proves to be a really useful library. So I will just define again a function g, a function of two variable, say x squared plus 5 times y, so two variables. This is g, let's see, g here. If I wanted to integrate, to make a double integral and solve it for the two variables there, so x and y, I will just type again the function integrate. I will just pass in the name of the function, so g. Then I will pass, as usual, x. Let's say we wanted to calculate the integral with, and we want to integrate with respect to x from -2 to 2. And then, since we want to make a double integration, the other integration is referred to the other variable. So we just open again the parenthesis, and we have like y, which is the other variable, from 3, let's say, to 5, for example. So this is how we specify the two variables and the two boundaries for the two variables of the integrals. And then we just press enter, and this is the result of this double integral. If we were to have like a triple integrals, we will have another parenthesis with the third variable and the third boundaries. So that's it. Even this time we solved the problems in a really easy and immediate way, just by using SymPy and just by using these functions, which I find really useful and I would say direct. I mean, it's just to type a command on your terminal and you get the result, which is really good, I would say. So let's switch to the next chapter or the next section of this tutorial, and in the next section we will learn how to calculate the limit of a function. Well, limits are basically mathematical functions that allows us to calculate the value of a function when it approaches some, let's say, critical points in which we are not sure whether it is defined, because in these points the functions can basically diverge or converge to specific values, or do some very unintuitive things. So it's really, I mean, sometimes also limits are really hard to calculate by hand, especially because you have quite always to remember some specific math rules for specific types of of limits. Sorry. So even in this situation, SymPy turns out to be a quite useful, I would say, a very useful library, and with this function. So I will not define any function, I will just type them directly into the function that allows us to calculate the limits. The function is called limit, and let's calculate this limit here. So let's say sine of x over x, and we just have to specify the function, which is this one, the variable with respect to which we calculate the limit, which in this case is x, and the number towards which the variable is going, so the number that the independent variable is approaching. So let's say, for example, this time 0. So you can see that is a critical point, because usually we cannot divide a function by 0. So, but I mean, the limit means that we're not evaluating this function at 0, but in a point very close to 0. So let's see how it works, and it has calculated the limits. And this function close to 0 results equal to 1. So this is how you calculate the limits with SymPy. There is another case which we can cover. Sometimes there are functions that have different values depending whether we are approaching a critical point from values that are lower than the critical point or higher than the critical point. So I normally refer to them as if I'm moving from the left towards the critical point, or from the right, decreasing the values towards that critical point. So we can use SymPy to solve also these situations. And a specific case is represented by the function 1 over x. So f is equal to 1 over x now. to solve this limit, you will see that the function will assume different values depending on whether on where we are from where we are approaching the critical point, which is in this case 0 for this function. So I just write limit. I will pass in the name of the function, so f. Then I have to specify the variable, which is again x, and then the critical point, or the point in which I want to evaluate the function, so 0. And let's say I wanted to calculate this limit while the independent variable, so x, is approaching the critical point 0, coming from lower values. So I will just add this, the symbol for the minus sign, like this, and you can see that the value of the limit is minus infinity. If now I want to calculate the limit of this function, but when the independent variable is approaching the critical points coming from higher values, I just change the sign here from minus to plus, and you can see that now the function, when we come from this way, the function values is plus infinity. So that was it. I mean, also in this case, as you can see, SymPy is really useful and immediate to calculate the values of these functions, and it's really easy. I think this is the main feature of SymPy. It's really easy and immediate in just solving also very difficult math problems. Because of course you can just have very difficult limits instead of just 1 over x or sine of x over x and so on. Okay, so we are just arrived at the last session. In this last session, I'm going to show you how to use SymPy for plotting functions. Also, in this case, SymPy has a lot of features regarding the plotting, a lot of options and so on. So yeah, I would just start by showing you how to make like a very simple plot. I mean, in this case, SymPy usually exploits matplotlib as a package to create the plots in a separate windows, but you can also do that without importing matplotlib. I will just show you the results. It's not that clear because the results will appear in your terminal, which is not the best thing actually for a graph. But I will show you anyway how it looks like. So we can just define a plot, p1, let's call it. And the function is really similar to matplotlib, it's plot. And we have to pass in the function that we want to plot expressed in the explicit way. So with all the independent variable terms on the other side of the equal sign. So for example, let's say we want to plot a line, which, I mean, the equation of line could be like y equal to something times x plus something. So in this case, let's see, 3 times x plus 4. This is the equation. So the equation of this line, it should be y equals to 3 times x plus 4, comma, and I will also, I mean, if you don't specify anything else, the default boundaries for the plots are, I think, -5 to 5, refer to the independent variables, so x, but we can also specify some other boundaries for x, and we just have to open a parenthesis and just type the independent variables, so x, and then the boundaries, so -3, 3, close the parenthesis, and as you can see, oh no, I had already installed matplotlib, so it has opened a matplotlib window with the graph on it, which is far better than the other one, because in the other case it would have created a plot by using like dots and lines, which is kind of not immediate and not really clear. But here you can just see that he just created a line in the plot, and the boundaries are -3 and 3 for the independent variable. So it was really easy. Next thing that I'm going to show you is how to add another plot to the same one. So now we have defined P1. We can just define another plot here. P2 equals to, again, plot. Let's say that we want to print, let's print a parabolic function, so x squared. Again, I want to define some boundaries for the independent variable, let's say 3 and 7. And then, since we don't want to plot this graph by itself, I will specify now this option, so show equal to false, which means that we do not want to plot immediately this graph. So we have just defined the plot P2. To add the graph P2 to the same window of the plot P1, we just have to use this function, which is called extend. So we just type P1.extend and pass in the name of the plot that we want to add to the first plot, so P2, and that's it. Now to show the plot, we just have to type P1.show, and hopefully, if we did everything correctly, we will see two plots now in the same window. Here it is. So we have P1 here from -3 to 3, and then we have P2 here, which is x squared, defined by from 3 to 7. Again, good. Another useful thing that can be done in SymPy is the thing of plotting like parametric functions, which are not strictly speaking mathematical function, like for example circumferences, which are really, I mean, they couldn't be plotted in like matplotlib arrays or something like that because they are not strictly functions. So to do that, we have a specific function that is called plot parametric. So we use that directly, plot parametric, and what we pass in is the equation of the function, and the equation is I have to open another parenthesis. So yeah, since it's a parametric function, we have to pass in the x and the y variable of all the parametric points that define this equation. So let's say in the case of a circumference, we have cosine of x for the x coordinate and sine of x as the y coordinate of the parametric curve. Then comma, and then we have to specify the boundaries for the x variable, which is the parameter in this case. It's not called a variable. So let's say -7, closing the parentheses, and we should be done. Oh yeah, as you can see, we have obtained a circumferences, and as the function, the x variable and the y variable are defined by two trigonometric functions like cosine and sine, the maximum value that they can take is 1 or -1, as you can see here. So this is the circumference. It doesn't look like a circumference because, I mean, the plot is not the same. It's not, I mean, a square window, so it's just from an optical point of view. So that's it also for this. The last thing that I want to show you is a method that allows you to solve the issue of entering the equation of the function in the explicit way, in the explicit form, sorry, because sometimes it's not that easy to calculate or to express a function in its explicit form. I mean, it's okay when we have like lines or parabolic functions, but sometimes the equation can be quite difficult to work around. And so to solve this problem, we have another, I mean, SymPy has another great function which allows us to enter the function in its implicit form. So as in the same exact way that we can find it, for example, in a problem. And this function is called plot implicit. So really easy and direct. And we just type in the implicit form of the function. So let's say, for example, x squared plus 2 times y. As you can see, we have both the variable in the same place. Well, here it would be just the independent variable. We have the dependent and the independent variable. So if we were to plot this function with plot, we will have to express like, it would be like epsilon y equals to minus x squared over 2, which in this case is easy, but when we have like logarithms or exponentials, it's not that easy. So we have to pass, as I was saying, the implicit form of the function here, and then as it was before, we have to specify the two variables in this case, so x and y, and their boundaries if we want to make some if we want to change from the default boundaries. So x, let's say again minus 2 to 2, and then again y from minus 3 to 3. We close and we plot, and here it is. Perfect. Also, this was really easy, I would guess, and as you can see, y is the dependent variable and x the independent one. As I told you, we can just also try to do this thing, but with using the function plot, just to see how it looks like, but it will be the same basically. So plot, the explicit form of this function, I may also express it wrong in the wrong way. It's, if I'm not wrong, minus x squared. Oh, sorry, I did a mistake. Minus x squared over 2. Yep. And then again, x from minus 2 to 2, comma, y from minus 3 to 3. Okay, let's see. Oh yeah, and yeah, it's almost the same. I mean, the proportion is a little bit different because we had more space here in the last time, but yeah, the ending result is the same. But the only thing that changed is that in this case, in this latter case, we had to calculate before entering the function its explicit form. So I think we're done for this tutorial. I hope that you liked the tutorial and that you find the function that I show you useful. And of course, these are not all the functions that SymPy comes with. If you're interested in other functions, in more advanced tasks or more advanced functions, just check the documentation. You can find it on the website. I just put it also the link in the article, and you can just have a glance at how many packages there are in SymPy and how much this library can do for you. It's really amazing. If I were you, I will have it a look. I will give it a look because it could be quite useful for basically all data science and I would say all the problems that you might encounter in your coding. So that's it. Hope you liked the video and see you in the next one. Bye bye.